Hello, and welcome back to another session on data mining. In this lecture, we are going to cover generative adversarial networks, which are being used to generate these images such as deep fakes or imitate a particular celebrity or something. But we are going to take a very simple approach to understand generative adversarial networks. And we're going to begin with a very simple generative machine learning example. And we've already covered that in a previous lecture as well. Let's say you have a natural process. In this case, consider the natural process of having a coin, and it doesn't have to be natural. It's a process that is outside of our machine learning model design. So that's why we call it nature. So that's where we'll be getting our data from. So let's consider a process in which you have a single coin, and that coin has a certain probability of generating heads, which is zero point 0.7, and it has a probability of generating tails, which is 0.3. But we don't know that. Okay, so that we as being observers outside of that process, we don't know what underlying probability distributions of generating heads and tails is. But what we do know is that this process is used to generate some data, and we can see that data. So think of it like this: you have a blanket between your nature and the underlying factors or the probability values involved in the process of generating data and yourself. And all you can see is the outcome, which is in this data form. So let's say if you have some data that has been generated from this process, it can be head, 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 tail, tail, head, and so on. So it can be a string of these head and tails, and this is all you observe. So the natural process generates some data, and then that data is what we are going to use to do modeling or density modeling. The goal of generative machine learning is to make a machine learning model that can generate data, in this case heads or tails, that follow the same distribution as the real world or the natural process. So let's say before we have a natural process, I'm going to call it nature or natural coin. Okay, and then you have got a machine learning equivalent of it. Now nature is spitting out these strings of head, head, tail, tail, and so on. And what we want to use is this data that has been generated to train a machine learning model that we call a generative machine learning model, so that it can also generate examples in much the same way. And those examples should have the same probability distribution as the original data that had been given to you. Or actually we want to imitate the natural process that goes on in this. So we want to imitate what is we want to use this machine learning model to generate or imitate a generation of heads and tails, so that you cannot tell whether this data was generated from a machine learning model or from nature. So the goal is to make a machine learning model that can generate data that follows the same distribution as the real world or natural process. So let's say if you've got two probability distributions, you've got a natural distribution of p of x, and then you've got a generative process that is generating these a machine learning based process that is generating the same data. The probability distribution of both of these should be identical. So let's say if you assume that you have a learning machine G which generates data, then the difference between the probability distributions of this natural process and this G should be small. So that is the real goal of generative modeling. So an ideal machine learning method for generative processes, let's say if you want to generate coin flips, would be uh, such that you're not able to discriminate between the data generated by nature or the data generated by the machine learning process. Okay, there can be two different ways we can do this. We can either model the density explicitly, or we can do it implicitly. What that means is essentially the following. So let's say we've got a generative process in nature, and then we have tried to imitate it using a machine learning model that I'm calling G. Okay, which can be used to generate examples like head, or data like head, head, tail, tail, and so on, right? So this process of generating that data is called sampling. So once we have a model of the natural process, we had a natural process, right, which was a probabilistic process that generated these samples, and we tried to imitate it using this generative machine learning model, which is now generating this data. And we've already talked about that the probability distribution of this should mimic the probability distribution being used in the natural process, right? If a machine learning model that we train, or the generative machine learning model that we train, can generate these samples, okay, so that's the first requirement for it to be generative. If it can also tell me what is the probability of observing a particular sample explicitly, so if it can tell me, for example, p of x is equal to head is, what is the probability? Let's say, is it 0.69? And let's say you have the probability of generating tails, which is 0.31. Okay, so this is pg. Okay, if it can tell me that, then what we say is that we have modeled the density or the generative density being used in nature explicitly, because now we have a model that can tell us what is the probability of px is equal to h, or px is equal to t, or so on, right? So we can get an idea of what is, how likely a certain sample is. Okay, and if your machine learning model can tell you that, we call it an explicit density estimator. There are examples such as variational autoencoders that we haven't covered in detail, but they are able to do this. So if you ever come up with a problem where you want to estimate, you want to generate data as well as you want to give explicit probability estimates of a certain sample, this is what you should be looking at. Now, if you let go of this requirement that you want to be able to generate the probability of x is equal to h, and you just restrict yourself to generating data, then what you can do is what is called implicit density modeling. So the machine learning process, or the generative process G, does not have an explicit model of the probability density, so it is not able to produce these values, but it can produce samples for you that would follow the same probability distribution as being used in nature. And generative adversarial networks are essentially a way of doing the same thing. They can generate samples, but they cannot typically give you how likely a particular sample is to be observed in nature. Okay, so that is the goal of these. If we want to develop a REO representation, or a representation, evaluation, and optimization for generative models, remember, we start off, for every machine learning problem that we have, we start with the goal, and to solve that, we express it in terms of representation, and we develop a loss function for it, right? So that is what we are going to do here as well. In order to make a machine learning model that is able to generate examples, generate data, so I feed it some random noise to the machine learning model as input, or I can input some factors as input. So let's say if I want to generate examples of a certain class, I can put that as input to the machine learning model so that I can get samples of examples for that, right? So this is what our representation is going to look like. We should be able to generate data. So let's say if you want to generate images, or if you want to generate 28 by 28 images, right? So your output dimensions for this machine learning model should be 28 by 28 or 784. On the input side, you can have a random noise as input, and then in between you have your machine learning model. So this is what these factors go in. This can be completely random noise, so that the machine learning process then generates an example for you. Okay, so this is what the representation is going to look like. Now the next bit is evaluation, and since our goal is to learn the parameters of the model so that the generated examples follow the same distribution as real world examples, the evaluation, or the loss function, can be the difference between the probability distributions of x in nature, which we call p of x, and of the generated samples that we call p theta of x. So let's say if we use we use this fz of theta to generate these examples, then the probability distributions p of x and p theta of x, one of them in nature and the other one that we have, should be minimized. So this is a very generic loss function that can be used for any machine learning problem, any generative machine learning problem. Okay, the goal is so that if I sample from P of X, so if I obtain a sample from nature, or if I obtain a set of samples from nature, or if I sample from P theta of X from my machine learning model, the real and generated examples are similar. Okay, so if I get a sequence of heads and tails from my machine learning model, and if I get them from nature, both of them should appear the same. And then we haven't expressed this mathematically, but the next step would be to express this mathematically. So it's important that you understand this evaluation bit, and then you can tune your parameters of your machine learning model, these theta, such that this difference is minimized using some optimization process. Okay, so that is the REO for generative models. What we are going to talk about is a very specific set of generative models called generative adversarial networks, which are pretty cool. First of all, it's I think one of the biggest breakthroughs in how we train machine learning models in general. This adversarial training bit. So in these generative adversarial networks, we play a game essentially. We have two models. One of them is called the generator model, and the other is called the discriminator model. The goal of the generator model is to generate examples. So this is going to be your G model that takes in some input noise, random noise, and it has a certain set of parameters that I'm going to call theta G. And what it does is that it generates a certain example. So let's say if you want to generate images from MNIST, then what this is going to do is that for a given random noise as input, it's going to generate an image that should look like an image taken from MNIST. So it should look like a digit. The discriminator, what it does is pretty interesting. What it does is it uses the training set of images that we have from MNIST and the image that has been generated. And what it tries to do is it tries to classify whether an image has been generated, in which case we call it a fake image, or is it a real image. So this is where discrimination takes place between the probability distributions of the generator, or what the generator has learned, and the underlying distribution from the training set. So we have these training samples that are given to us, and these samples that are being generated by the generator. Now, in training, what we do, so let's first of all call this D of X, and it has these parameters. Let's call those parameters theta of D. So it takes in a certain example as input, X, and says whether that example is real or fake. So in case of real examples, let's say we want to produce a label of +1, and in case of generated examples from the generator, we want to produce a label of -1. Okay? So the discriminator is able to do that for us. It has access to all the training data set. The generator, if you note, does not have access to all of the samples in the training data set. It just uses these random noise and generates a fake image or an image that should mimic the examples in the training dataset. The discriminator has access to the training dataset, and it uses that training dataset to learn whether an input image that is given as input to this discriminator belongs to or follows the same distribution as this training dataset, or it does not. So we have a discriminator and we have a generator. Now we want to train both the discriminator and the generator in such a way that the generator tries to generate images that look or that look similar to the images in our training dataset, so that the discriminator is fooled into thinking that these images that are generated by this generator process uh, are actually are not fake but real images. On the other hand, we want to train the discriminator in such a way that it is able to pick up any fakes. So, and then we use this signal of this real or fake to train both this theta d and theta g. Okay, so think of both of these as neural networks, the generator and the discriminator, and all the weights of the discriminator and the generator are called theta d and theta g respectively. And what we are trying to do is we are trying to optimize both of these weights, this theta d and theta g, based on this sort of a game that we are playing. We sample our images. The generator produces some images, or as we call them, we sample some images from the generator and we pass them on to the discriminator. So the goal for during training, we know that these images have been generated by the generator, so they should be classified as fake, whereas real images that we have access to or the discriminator has access to, those should be classified as real. Okay, so we tune the discriminator to generate these prediction labels. So theta d, or the parameters of the discriminator network, are optimized in such a way that it learns to classify between these generated and these real images. Okay, at the same time, we want to train the generator so that its generated images are able to fool the discriminator. So they have a sort of a competing goal, this discriminator and generator. So the generator tries to generate examples that should look like real images so that the discriminator is fooled into classifying them into the real class, whereas the goal of the discriminator is to do the exact opposite, that is, try to classify fake images or generated images as fake and real images in the training data set as real. Okay, and if we train it like this with these goals, we train both the discriminator and the generator like this, what we should expect at the end is that the generator would learn to generate data that fits the unknown underlying probability distribution of a training set, whereas the discriminator is now, if the generator has been trained perfectly, it is not able to discriminate between images in the wild or the real images and the generated ones. So this is the sort of a min-max strategy or the game theoretic strategy lying at the core of generative adversarial networks. The great thing about these generative adversarial networks is that you don't need to model the probability distribution of the natural process. It is being implicitly modeled in the discriminator to discriminate between the two classes, and that knowledge is used to train the generator to generate these images again in an implicit manner. There is no explicit probability density learning taking place, at least in the original versions of these networks. So that is what they do. They have a large number of really impressive applications. They can be used for synthetic image generation. So let's say we want to generate an image of an 8 or a 7 or a 6, they can do that. They can do so much more over and above that. You can do translations. You can have images. You can have neural networks to generate handbags in different styles by giving an input that looks like this. So you give a hand-drawn structure, and that is used to generate these images that look like seemingly real. You can generate these synthesized scenes. You can do style transfers. I posted some links to help you understand what these are. You can do speech generation, or you can do deep fakes. You just search the internet for deep fakes and you'll find all sorts of stuff there. Okay, and it opens all kinds of these ethical dilemmas as well of what is real and what is fake and so on. But the main goal of what these do, these generative adversarial networks, what they do is that if you give them enough real world training data, let's say if you give them images of all the apples out there, then these should be able to generate images of apples that actually do not exist. So if you give them images of faces, they can learn what faces look like, and then they can generate these faces for you of people that really do not exist. If you want to understand these further in a bit more detail, I would strongly recommend that you take a look at this excellent tutorial by Ian Goodfellow, the creator of generated adversarial networks. And there are some really cool tools and applications available. There's something called the GAN Zoo, and I posted a link to that here that allows you to understand how these GANs work. There are so many different types of GANs. There are unconditional GANs, and then there are conditional GANs, and we're going to talk about briefly about those. But first, what we are going to do is take a look at how we can code a very simple generative adversarial network.